I hope you can still see my screen. Hello.
Yes, we can.
Good. So let's
Yes.
quickly discuss about the vertical and horizontal asymptotes. We shall begin by giving the definition and do an example. So the line y equals to b is a horizontal asymptote of the graph y equals to f of x if f of x gets closer to b as x gets closer to infinity or as x gets closer to minus infinity. And then the line x equals to a is a vertical asymptote if f of x gets closer to infinity or f of x approaches minus infinity as x approaches a from the left or as x approaches a from the right hand side. So I'll draw a diagram to explain that. Assume this is our x, y plane. And I have this line, call it x equals to a. And I have this other line. Y equals to b. So this is an arbitrary function. F of x. It's an arbitrary function. So this red line is what we call the horizontal asymptote while this greenish line is what we call the vertical asymptote. So vertical asymptote are these lines such that the value of the function, they are vertical lines such that the function appears to be either growing larger and larger. The function appears to touch those lines as you either make the value of the function larger or the value of the function smaller. Like in this case, this green line, what you are calling the line x equals to a, is a vertical asymptote with respect to this function, these two curves I've drawn here, because the value of the function as you try to go towards that line from the right-hand side, you see the value of the function will be growing. I just extend this one to see it clearly. I remember you can extend this also. So there are this arm A, there's this arm of the function B. So to approach the line x equals to a from the right-hand side, we are going to move along the line, along the curve A. So as we try to get closer to this point x equals to a, then the value of the function appears to be growing larger and larger and larger. But the line, this vertical line and the graph will not touch each other, but they appear to be getting closer and closer to each other. But then the value of the function grows larger. Similarly, as you try to approach this line x equals to a from the left, then you'll be moving along this curve, and this curve grows to the negative sign or negative side of the line x equals to a as you try to get closer and closer to the x equals to a line. Similar to the horizontal asymptote, these are the lines which are horizontal lines where the graph appears to be approaching or getting closer, but they don't really touch each other. So note that the value of the function is not defined at x equals to a. So it only appears to get closer, but it's really, you don't get the exact value of the function at a itself. So as a quick example, evaluate find the vertical and horizontal asymptotes, if any, of the following function. And the function is f of x equals to 4x minus 5 divided by 3x plus 2. So to solve this problem, you just remember that for horizontal asymptote, we simply evaluate limit as x approaches plus or minus infinity of f of x, which must be a number, say b. And so the horizontal asymptote is y equals to this number b. So that's what you do. It's like us asking you simply find the limit of the function as x approaches either plus or minus infinity. And if you get it is a number, then it means that the horizontal asymptote for that given function exists. In some cases, it may not exist. So here, when we find limit as x approaches, say, infinity, of 4x minus 5 over 3x plus 2. You remember how we were playing with this kind of stuff? You remember how we used to evaluate limits at infinity? What are we supposed to do? What did I say we are supposed to do?
Divide each term by the highest value of x in the denominator.
Correct. Divide each term by the highest x in the denominator. So we're going to have limit as x approaches plus or minus infinity of 4x. Remember the highest is x, so over x minus 5 over x divided by 3x over x plus 2 over x. Which would be limit as x approaches plus or minus infinity of 4 minus 5 over x over 3 plus 2 over x. So limit as x approaches plus or minus infinity of f of x will be limit as x approaches plus or minus 4 of plus or minus infinity of 4 minus 5 over x over limit as x approaches plus or minus infinity, but this infinity of 3 plus 2 over x. Just applying the limit properties. And I hope all of us can see that that would be the final answer. Are you able to see that where the 4 over 3 is coming from? If you work out the whole step.
Yes.
Good. So therefore, the horizontal asymptote is y equals to 4 over 3. So if you are to sketch that graph, you'll see that the graph cannot touch the line y equals to 4 over 3. It only appears to get closer and closer to 4 over 3. So for the vertical asymptote, it's as good as solve denominator equals to 0. So we are saying denominator equals to 0 because now what determines the vertical lines which are not satisfied by this type of rational functions are those values of x which do not define the denominator or give you undefined value for the denominator. So in our case, we have f of x is given by x minus 5 over 3x plus 2. So when you solve, pick the denominator and equate to 0. So what will be the value of x? But for the value of x will be
2 over negative 2 over 3.
negative 3 over 2. Is it 2 over 3 or 2 over 3? Okay. So then that becomes the vertical asymptote. So if you ask about vertical asymptote and you're given a rational function, it's a very easy exercise. Take the denominator, equate to 0 and solve for x. So that will give you the vertical asymptote. If you're asked of the horizontal asymptote, simply means pick the function, define the limit as you approach plus or minus infinity. And it will only be a horizontal asymptote if the limit of the function as x approaches plus or minus infinity will give you a real number. So as just as an appetizer, in relation to what we did last time, if someone asks you find this limit as x approaches 3 from the right hand side of 2 over x minus 3 and limit as x approaches 3 from the left hand side of 2 over x minus 3. So remember, just as we explained, when you are defining the left hand and right hand limits. So this is what you call the left, this is what we call the right of this number 3. So if the first case, x is close to 3, but larger than 3, then the denominator x minus 3, is it a positive or a negative number?
Positive.
Positive, correct. It's a small positive number. And so this fraction is a large positive number. That should make sense. You know that if you are defining a fraction a over b, if you fix a and you change b to be a very small number, then the quotient will give you a bigger value. Do you see the sense in that? Are you able
Yes.
to picture that? That you have a fraction a over b. If you fix a to be the same number, you are not changing it, but you make this b to be a very small number. The overall or the global effect is that your value of that fraction will be bigger. Okay. So does this intuit mean limit as x approaches 3 from the right hand side of this fraction is going to be positive infinity. So positive infinity sign used to show a very large positive number. Similarly, if we approach x equals to 3 from the left, or this same thing as saying, if x is close to 3, but smaller than 3, so meaning that you're moving now from this other direction, then what are we expected to have as this difference? X minus 3, will it be negative or positive?
Negative.
Negative, correct. Is a small negative number. And so 2 over x minus 3 is numerically a very large negative number. And so the limit as x approaches 3 from the left of 2 over x minus 3 is going to be a very large negative number. And clearly, x equals to 3 is the vertical asymptote. If you were to sketch this, you'll get such a graph. So this is the line x equals to 3. So that's how the graph f of x 2 over x minus 3 will look like if you had to draw it. So in this example, also the line y equals to 0, x-axis is the horizontal asymptote. So some important limits. Please read the handouts I shared to appreciate how these results are obtained. I'll state them without proof, and they'll help us to do some problems when it will come to differentiation. So ensure that we check how this is obtained. Limit as x approaches 0 of sine x over x is always 1. Number 2, limit as x approaches 0 of 1 minus cosine of x over x is 0. Keep in mind of those limits. They will help us to solve some problems in future when we'll be doing differentiation. So for instance, someone can ask you, what is the limit of sine 4x as x approaches 0 of then sine of 4x divided by x? So quickly to solve this, you can say let you make a change of variable theta, they're given by 4x. So this means that x alone will be
theta over 4.
theta over 4. And so we are going to, it's like we are going now to change all this limit from having variables x to new variable theta. So then now, when x approaches 0, then theta approaches which value? I remember approaching 0 is as good as for you to get the interpretation. If you are to be at 0 itself, what would be the value of theta? If theta is 4x. Zero still. So which means this where theta is approaching and where x is approaching, they have the same things. And then which means sine of 4x over x is the same as sine of, where there's 4x you put theta, where there's x you put theta over 4. And are you able to see that this will be the same as 4 sine theta over theta? Are you able to see that? Yeah, good. So which means limit as x approaches 0 of sine of 4x over x is the same thing as writing limit of sine cosine theta over theta as theta approaches 0. And we did properties of limits. This we can drop out the 4 because it's not affected by theta. So what do we end up with?
One.
1 for this limit, and then you multiply by 4. So all this part is 1. And so you have 4 times 1, which is just 4. So I want you now to try on your own what would be the limit as x approaches 0 of sine of 9x over x. B, limit as x approaches 0 of sine of x over 5x. And lastly, C, limit as x approaches 0 of sine 3x over sine 7x. Tomorrow we'll discuss continuity, and then from continuity we start differentiation. I wish to stop at that point, or should we continue with the remaining 7 minutes?
Yes.
So that's enough.
I believe that's enough.
Oh, good. Yeah. So that's enough. So keep it up. Do as many examples as you can, and ensure that you remain the A student that you have always been. I checked at your papers. Some are trying, some are not
It's
trying.
not enough.
So ensure that you